Hey everybody. Okay, so this is what we're going to try to do um, to get through these R notebook tutorials in a little bit better way here. So what I'm going to do is first walk you through the knitted PDF file so you get a sense of what the objectives are, and then from there we'll go briefly through the code, and then the plan is that everyone would look at this code on their own, see if they understand what's going on, see if they're confused, and then we'd have a chance to talk about it in class. So let's just get started. So this is associated with lecture 4, although we're really going to be touching on some ideas that we're going to use later on in the semester as well. So let's see. So what are we going to do? We're going to see how functions work in R and see how you could write your own function. We're going to see a simple example of a for loop. We're going to evaluate a simple ET model and then see actually that that ET model doesn't work very well, but that we could actually calibrate it using some sort of optimization method. And so to get started then, a lot of the things that you've been doing in R has been using functions. So anytime that you type something like this, so in this case SD parentheses X, that's a function. So this is the function that calculates the standard deviation. And so you could actually look and see what the contents of that function, meaning the R code that it's actually running, is. So if you just type SD, no parentheses there, it'll spit out the actual code that it's running. And so here it's not too bad, but if you were to look at a more complicated function, that code might look pretty crazy. So one thing that we're going to do in a minute is see how we can write our own function. And what we're going to do is write a function to implement the Blaney-Criddle formula for estimating reference evapotranspiration. And let's see. So just to remind ourselves here, P is the percentage of daylight hours ranging from 0 to 1. And then T mean is the mean daily temperature in degrees Celsius. Okay. And there's some stuff here that you can see. Basically, we say that, when does this equation work well and when doesn't it? So first thing we're going to do is read in our FlexTower data set. This is the same thing that we used in our example, or in our example from lecture 3. So reading this in should look pretty familiar at this point. And what we're going to do is pull out all the data from 2014 again. Oh, sorry. Okay, so that's what we're doing. And here you can see the daily evapotranspiration plotted for 2014. And then here what we're doing is just quickly converting that from latent heat in watts per meter squared into evapotranspiration in millimeters per day. Okay? So here we have the same plot, but in millimeters per day. So far, so good. So then we have the actual function. And so this is the general sort of way that a function should look. So, the name of the function, and then here you say that it's a function. And these are the arguments that you're providing to the function. So that P value and that mean temperature. And then inside the function, you do the calculation you want, and then you return the answer. So first of all, you can just type the name of that function without parentheses, and it'll just spit that code back to you. And then you can enter some values for P and for T mean. Of course, we don't have any idea whether those numbers don't correspond to any particular day. They were just chosen at random. And so we would want to actually see, for example, whether we can predict something like that looks something like this, but using the Blaney-Criddle formula rather than the latent heat observations from the tower. And so the hard part here, and the part that I don't want you to get too bogged down in, is how we compute this value of P for each day over the course of the year. It's pretty ugly and not all that enlightening, but that's basically what the next couple blocks do here. So we need a new, or there are multiple ways to do this, but the way that I chose to do it was using a new library. And then we basically find the difference between sunrise and sunset in hours, or actually in decimals of a day, and then finally this daylight is giving us that fraction. Okay, and so let's see. So we do jump around a little bit here. So I want to show you quickly what this for loop is all about. Actually, it's just a very quick intro, and it's worth, if you've never seen this stuff before, to take some time learning it on your own. So I just have a very quick example of what one of these does. So I've defined 3 variables here, and here we're looping through 10 different iterations, 10 different times through this for loop. And what you should do is take a close look here and see if you can understand what these variables are doing as you're iterating through this for loop. And so it's always good to, what I would say is run the code and then see what X, Y, and Z look like, I guess first before and then again afterwards. Okay, so from there we finish. We have to actually use a for loop, or at least I needed to use a for loop to figure out a way to find the daylight fraction for every day. And so then after that's done, this is the plot of it. And so you can see it starts low in the wintertime, goes high in the summertime, and back down again. And to me, these numbers look like they're probably more or less okay. So now we have 365 values of P. The Flux Tower data set has values for temperature, so we can use that directly. And so we can enter those into our Blaney-Criddle equation, and you'll see the results. So here's an example of how you would plot multiple lines together, and so this is what you get. So the red is showing the Blaney-Criddle equation results, and the black is showing the results from the Flux Tower, and they don't look very good, do they? So Blaney-Criddle seems to really be overestimating things, and so we can assess that visually, but in principle you could also assess that using some sort of metric. And there are a lot of things that end up getting used for this, but some examples could be what we call mean squared error, so MSE, or the mean absolute error. So if you've never seen these before, it's worth Googling them. You can look them up on Wikipedia, for example. But this is putting them into practice. So we've taken, the Flux Tower observation, the Blaney-Criddle ET minus the Flux Tower observations squared. The mean of that gives us the mean squared error, the MSE. In contrast, if we take the estimates minus the observations, and of course you get the same answer if you did this the other way, then you take the absolute value, then the mean of that, you get the mean absolute error. And so you can see the values for these two errors here. Okay? And so you could use those to quantify all sorts of different, anytime you're comparing, models against observations, for example. And so, we don't like this plot very much, and so the question is, what can we do about it? And so one thing that we could try doing is saying, actually, those coefficients, let's see, where is it? This, let's go all the way to the beginning, this 0.457 and this 8.128, maybe those need to be different in this forest in northern Wisconsin. We don't know where those came from, so let's try doing something on our own. So we're going to say, okay, those are A and B, and we want to find out what A and B should be for a forest in northern Wisconsin. And so we're going to do that. And so one way that you could do it is to create a new function. Here we're calling it Blaney-Criddle underscore mod. And here we've included a and b as new arguments. So those are things that you're going to need to provide to the function now. And you can see that now a and b show up rather than those coefficients that are used originally. Okay, and so this is just an example of this. We've provided a couple of more numbers. And so then the question is, what values of a and b should we use? Well, one way to do it would be to try guess and check, right? So if you tried enough times, you could probably find something that did a better job of fitting closer to this black data. But that's not ultimately where we want to end up going. So what we're going to do instead is try to find optimal values for a and b. Now, this is where things get a little complicated, and I want to see how people sort of feel about it before we go into a lot of the details. But essentially what we're going to do is what's called an optimization. And this does get a little ugly. So we're going to define a new function that's going to be called calibrate underscore Blaney-Criddle. It looks pretty much the same with a few exceptions here. So just because of the way this optimization works, as you'll see in a minute, we actually had to put a and b into a single vector. So now this pars stands for parameters. It holds both the values of a and b. Then we have p, we have t-mean, and we're putting our observations, our ET observations, into it as well. So we use we use the first entry in pars, which is a, the second entry in pars, which is b, p, and t-mean. Okay, so then we calculate our Blaney-Criddle evapotranspiration like before, and now what we do is we define what we call this objective function, or just shortening that here. And what we're doing here is actually finding the mean squared error of the Blaney-Criddle evapotranspiration versus the observations, just like we did before. Okay, just like we calculated mean square error before. And then we are returning the value of the objective function, not the value of evapotranspiration. Okay, and so then you can call that and, for example, get a number like this. You could, so here we're putting in the original values of A, original value of B. You could change one of those values, put in the original value of A, but a different value of B, and it's going to give you the mean square error. So we're actually moving in the right direction, right? We put in 4 instead of 8.125, and our mean square error went from 27 down to about 12. And so this is where things get a little wild, and let's just see how it goes. So we're going to use this optim function, which is, stands for optimize, basically. So in order to do this, and there are different ways to set this whole thing up, and unfortunately it's cut off a little bit of the code for us, but I think we can see the most important parts here. So you need to put in initial values for your two parameters, A and B. And so we'll just use the original ones, but you could pick something else. In some cases, it's really, really important what initial values you pick. Ideally, you want them to be based on some prior experience or some sort of knowledge. You want them to be somewhat close, like the right order of magnitude, positive instead of negative, that sort of thing, to what you think the final values are going to be. Okay, so we're putting that into our optim function. We're putting the calibrate Blaney-Criddle function into our optim function. What this is doing is defining lower and upper bounds for A and for B. So the bounds for A are going to be 0.01 to 1, meaning we're never going to get a value greater than 1 or less than 0.01. And then the bounds for B are going to be between 1 and 20. So the answers that we get, the optimal values of A and B, will be somewhere within this range because we've constrained the problem in that way. And then over here, we're just providing the rest of the arguments that are needed for Blaney-Crittall. And so then you just run this and you get these numbers. So this is the optimized value for A, this is the optimized value for B, and this is telling you the optimal value of your objective function, meaning that the mean square error of our optimal model, meaning using these optimized values of A and B, is 0.86. And so that is a lot lower than 27, right? Okay, so let's just see how they look then. So we're going to replot everything. We're going to plot our original Blaney-Crittall estimate. We're going to plot our Blaney-Crittall estimate based on the calibrated values. And then we're going to plot our values from the flux tower observations, and we'll see how we did. Okay, so black is our observations, red is the Blaney-Crittall original, and then blue is the calibrated Blaney-Crittall. And it looks, pretty good. Not perfect, it seems like maybe it overshoots things a little bit on these shoulder seasons in the spring and then again in the fall, but more or less we're doing reasonably well. And so, that's not too bad, and what we're going to try to do later is learn using some more complex hydrologic models that do more parts of the hydrologic cycle, specifically using the our hydro package, how to calibrate a model, how to calibrate that model using this exact same sort of approach. So in retrospect, I realize now that I went through all the code in detail here in the PDF, so I'm not going to go through it again in the R notebook.rmd file, but what I would recommend that you do is go through that file on your own. See if there are things that you understand, things that you don't understand, things that you'd like to talk more about, and then we'll have the chance to talk about those things in class. Okay, so thank you very much, and I hope this format works well for everybody.